Hi everyone and welcome to Chem class. Today I want to talk to you about acids and in particular how we have a classification of acids in terms of their strength. So first of all, let's just check over our definition of an acid. So according to Bronsted-Lowry definition, an acid is a substance that will donate a proton, and that proton being an H plus ion, because essentially all it is a proton. So if I'm writing an equation to show a substance behaving as an acid, I take my hydrochloric acid, which is my first example here, and I'm just going to put it with water, and we'll keep it the same in both the examples. And the HCl will donate that proton, that hydrogen ion, and what we get is a Cl minus, and the H2O will actually pick up that proton and turn into the hydronium ion. So this is an equation that shows that HCl is acting as an acid. But the other thing I want to talk to you about today is what it means to be a strong acid. So the definition of a strong acid is something that completely ionizes. What does that mean? It means that every single HCl that I have in this particular vessel, let's put with the water, every single one of them will do this, will donate a proton. And I can indicate that with a single arrow. The single arrow means everything on this side has turned into what's on the right-hand side, and the reaction stops once it's done that. So the HCl donates the proton, becomes a Cl minus, and that's the end of that. It won't do anything further. It won't go in reverse or anything like that. So it completely ionizes. So to recap, if I had 100 of these HCl molecules, every single one of them, all 100, would turn into 100 Cl minus ions and 100 hydronium ions. Let's compare that to something that we consider a weak acid. So a weak acid, and the definition you have probably seen of that, is something that partially ionizes. So a weak acid such as carbonic acid, H2CO3, again, I'll put it with the water. The difference here is that, again, let's say I had 100 of these, 100 H2CO3s, not all 100 will actually donate the proton that we know it can do because it is an acid. So remember, the definition of an acid just means it can donate a proton. It doesn't mean that every single one of those molecules that is an acid will do it all the time. So the H2CO3 in the water, because it only partially ionizes, or not every single one of them will completely donate that proton and then end it there, we indicate the partial ionization with a double-headed arrow, like so. So it is different. We can see in the equation, just by looking at the way it's represented, that we have a strong acid that completely ionizes versus a weak one that partially ionizes. So we're still showing what it's making. It when it donates the proton, this will become HCO3, the 1 minus, and we'll still create some hydronium ions. But the difference here is that of the 100 I have of these, let's say, maybe there's only 10 of these created, or 20 or something like that. Only a small portion of the 100 will actually go and do that. There's no way of knowing from the way this equation is represented what percentage. We don't have that information at this stage. So what does this mean in terms of concentration and of pH? Well, pH is not a measure of the concentration of the actual acid molecules. No, if you've seen the formula for calculating pH, you'll know it has got to do with the concentration of hydronium ions. So that means that when you are testing the pH of a substance, it's actually measuring the concentration of H3O plus ions. Both the equations, both the acids have created H3O plus ions. However, because the HCl completely ionizes, for every single one of these, you're creating one of those. But over here, because there is only partial ionization here, it means that for the H2CO3, you'll only get a small amount of these. And that will reflect differently in the pH when you are actually testing that in the lab. Hope that helps.